one of the best parts about working at the Exploratorium is that we are kind of chummy with a lot of science organizations, and NASA is one of those. So we get to have access to a lot of the wonderful scientists and communicators who can come and tell us more about the work that we're doing. Brian Day is no exception here, as one of our wonderful guests who can teach us a lot more about what's going on up there on the moon. So he's based down at the NASA Ames Research Center, and he's part of the Solar System Exploration Research Virtual Institute. And specifically, he is the project manager for the Lunar Mapping and Modeling Portal, which is some incredible bit of software, which we're going to learn a lot more about. But help me welcome Brian Day.
All right. Thank you very much. And as Sam mentioned, 50 years ago, things were getting really exciting. We were about to send the first people to the surface of the moon. Imagine, if you will, imagine you are lying on your back, strapped in to a very small space capsule with two of your very close friends on either side of you. You are sitting on top of a big rocket full of high explosive, the size of a skyscraper. You are about to be the first people to be blasted off the surface of the Earth to ideally land on the moon. You're pretty good at math. You needed to be to get the job. And you've calculated your odds of surviving this adventure as something less than 50%. You've seen several of these rockets explode in very spectacular ways. You had 3 of your good friends incinerated aboard a fire on a previous Apollo mission. And there you sit. What in the world were you thinking? One of the astronauts, the commander of the later Apollo 14 mission, a gentleman named Alan Shepard, was actually America's first astronaut, the first American to fly in space. And after he came back from his pioneering first trip into space, a reporter asked him, as you were lying on your back on top of that big towering rocket about to be blasted off into space, what was going through your mind? And his classic response was that this thing was built by lowest bidder. These were very special people who made these trips, no doubt about it. And they went to some very special places. And word has just come down this week that we're going back to the moon. No, we're going forward to the moon, because we're going to do so in a sustainable way. So what I'd like to do tonight is take a look back at some of the places, in fact, looking at the Apollo landing sites. We will fly there, we'll take a look at them, and discuss what we learned there, why we went to those specific locations. And then we'll jump ahead and we'll look at where are we planning to go next. This is your sneak preview. And to do that, I'm going to use some software that my team at NASA develops. This is used for mission planning, for lunar science, planetary science, but you can use all of this at home. It's all web-based. You don't buy anything, you don't install anything, just point your browser to our URL, and you can do everything that I'm going to show you tonight and more. So we'll start out using our lunar portal. We have actually multiple portals, but we're going to concentrate on the moon. And you can pan, you can zoom, and let's head, oh look, here's the crater Tycho, nice big crater. One of the first things you might want to know is, well, how big is it? And with our Moon Trek portal, it's very easy to calculate distances, to measure distances. You just draw a line between any 2 points, and here it'll come back and tell you, wow, 83.7 kilometers, that's a big hole in the ground. Let's draw another line. This time we'll go across the crater, kind of extending on either side of the rim. And what we can do this way, this is really cool, is we can generate an elevation profile. Let's kind of move the moon out of the way there, and we can just kind of move ourselves along the profile there. So we can measure the heights of mountains, the depths of valleys. That's pretty neat. You can do your own lunar exploration very easily. So, but as they say on TV, but wait, there's more. So what we're going to do now, you can draw a bounding box around any piece of terrain you want. So we'll just draw a bounding box around Tycho here. And now you have the choice of generating an STL or OBJ file for your 3D printer. Yes, you can make 3D prints of whatever surface feature strikes you. Oh, that's so cool. But it gets even better. We've got a new tool we've just added, and this is really fun. You can just draw a line across any place you want, and you end up getting a QR code. So you draw any path you want, you get this QR code. Scan the QR code into your smartphone. Then take your smartphone and put it in a pair of cheap Google Cardboard goggles, and whatever path you just drew, you will now fly in virtual reality. Very fun. So now what we'll do is we will use Moontrek to explore the Apollo landing sites. Oh no, actually we won't. I'm going to show you one more really cool thing. Because what Moontrek allows you to do is to actually see the moon through the eyes of many different instruments aboard many different spacecraft. And we'll illustrate that by going here to the Marius Hills, one of the most spectacular concentrations of volcanic cones on the surface of the moon. Isn't that amazing? Look at that. Not so much. And this is taken with a really, really good camera, but they're just not showing up. But what we can do is change our view from a regular camera to a laser altimetry view, and boom, there they are. The volcanoes just jump out at us. Oh, that's pretty neat. Okay, let's try this again. Let's try something else. Now we'll go ahead and load a gravity map of that same area. Red is high gravity, blue is low. Looks entirely different. But what's really fun is with Moontrek, you can get a bunch of different data layers, stack them, and blend them. So data from different instruments on different spacecraft, even from different nations. And here we've blended the laser altimetry and the gravity map. And by doing so, we can now see the surface topography of the volcanic field and also visualize the now solidified unerupted plug of magma beneath the volcanic complex. Cool stuff. A lot of cool exploring. Now, this is a manual, somewhat artistic process, and it's quite possible that when you discover something like this, you might want to save it or even share it. And since this is all web-based, it's really easy to do. Moontrek will generate a URL for you. You just copy that URL, email it, text it to your friends, whatever. They can load that URL into their browser. It'll bring up Moontrek, load the layers, pan, zoom, adjust the transparency, recreate the view you just had. Okay, so now we're going to go to the Sea of Tranquility, the landing site for Apollo 11. And this place was chosen for a very special reason because it is one of the flattest, safest places to land we could find. Coming in, and the guidance computer tried to land us in that. West Crater, the size of a football field, houses the site of boulders. Neil Armstrong took manual control, flew to the west, and landed right there. You can see the descent stage of the lunar module. You can even see those dark lines, the footprints of the astronauts. Pretty cool. Apollo 12 landed in Oceanus Procellarum, the Sea of Storms. And what they did here is they decided they wanted to demonstrate a pinpoint landing. There's the lunar lander. We follow now the footprints of the astronauts as they journeyed and investigated a number of craters. But the crater that they were really interested in was this one right there. And I've got it with a mouse draw. That is the robotic Surveyor spacecraft that had landed a few years before, and they dropped down right next to it. Apollo 14. Now this landed in the Fra Mauro area, rolling hummocky hills caused by ejecta from a giant impact that formed the Imbrium impact basin. And so this was all pulverized rock that had been tossed out by this gigantic impact. And so they came down and landed in this much rougher area, and then they hiked up a ridge, a steep ridge, looking to get to the edge of Cone Crater. But because the ridge was so steep, they couldn't actually see Cone Crater, and they never got to the edge, but they got close enough that some of the rocks they picked up had actually been excavated by Cone Crater. Remind me to talk to you about that at the end. Apollo 15. Now we're heading down to the edge of that Imbrium basin that formed all those rolling hills, but now we're dropping down the edge, and the edge of the basin there is marked by these beautiful mountains, this beautiful mountain range that stands about the height of the Alps here on Earth. And as we look, we see coming into view there on the left, this long sinuous valley. Looks like an ancient river valley, but no water ever flowed there. This is formed by flowing lava. And from the heights of Mount Hadley Delta, the astronauts had an incredible view of this canyon. They were able to sample lava rock from the floor of the basin down below, and then much older highlands rock as they went up the slope of the mountain there. Now we had Apollo 16, dropping down into the true lunar highlands. So there's two different types of terrain basically on the moon. The dark lunar seas, which are areas of lava flows, and then this much rougher, higher highland terrain, much older material. So here we're sampling the oldest material that we had yet encountered. And so flying down, and this was now a much rougher area, much more difficult area to land. But astronauts Young and Duke can negotiate it successfully. And we can pan up from their landing site to North Ray Crater in the distance, and we can see they drove their car. Yes, they had a car, and they drove the car over to North Ray Crater and sampled material that had been excavated by the impact that formed that crater. Our last Apollo mission to the moon was Apollo 17. At this point, we're getting bold. We head toward the Taurus Littrow Valley, deeper than the Grand Canyon. As we approach this valley, you can see a fault scarp going across. You can see a light landslide. From the landing site, we'll pan up and look at the mountains. We can see boulder tracks where boulders, giant boulders rolling down the sides of the mountains there. Pretty spectacular area to go to work. And here on the edge of South Massif, we look out at the scar of this great landslide extending 6 kilometers out across the floor. So the lighter colored highland material going across the darker lowland basalt. And we head over toward Shorty Crater that excavated beads of volcanic glass that had been erupted in a fire fountain long ago. This was the first time we actually had a geologist on a mission, our first professional scientist. Looking ahead, where do we want to go next? This is one of the places. This is Reiner Gamma. This is an example of a lunar swirl, these weird patterns of light and dark. But it's absolutely flat. It's just different degrees of reflectivity. The moon has no global magnetic field, but this is an area where there's a localized magnetic field, and those light and dark swirls trace out the field lines. What causes that localized magnetic field? We don't know, but we want to find out. Here are our friends, the Marius Hills. Yep, we want to go there. This beautiful volcanic complex, about 200 or so cones and domes of volcanic nature. You can see a lot of those kind of beautiful lava channels cutting across. This area experienced prolonged volcanic activity over a very long time, and so it'll give us a chance to really understand the changes in the interior of the moon. Now we're heading down to an area, a completely flat, featureless area there in the middle of the screen. This is called the P60 basaltic unit. And this is what we think may be the youngest volcanic flow on the surface of the moon. Only about 1 billion years old. Now we'll rise up, and above it, here we have the Aristarchus Plateau. Again, an area of spectacular volcanism. You can see that long channel, and at the right, you have what's called the Cobra Head, volcanic vent 10 kilometers across. Dark areas of volcanic ash blanketing the terrain. Now, Most of the volcanoes, as we saw on the moon, are not very spectacular. That's because lunar basalt, when it erupts, is very low in silica, very fluid. It only has the viscosity of about olive oil at room temperature. Hard to build a mountain out of that. But in a few places, lava erupted thick and pasty and built tall, towering volcanoes like here, the Grutois and domes. Why was the lava here so different? We have no idea. Here's another interesting volcanic area. This is the Aina caldera. And as we look and measure the frequency of volcanic or of impact craters between those rounded hills, we see that that kind of rough area in between is an almost complete absence of impact craters, indicating very young terrain, less than 100 million years old. That could be recent volcanism. The moon is covered with impact craters, but that's not the only kind of holes we find. In certain places, we find these lunar pits, steep-sided pits that seem to open up into vast voids beneath. We think that these are actually skylights, collapsed roofs into vast subterranean lava tubes. Some of these tubes could be big enough to house cities. This is the Rima Bode area, and that dark area in the center is a blanket of volcanic ash. And that volcanic ash seems to be very rich in water. That's important because getting water to the surface of the moon is something you're going to need if you're going to live and work there. It costs about $100,000 a gallon to get water from the surface of the Earth to the moon. If we can find water on the moon, that's worth more than its weight in gold. This is the Orientale impact basin, big multi-ring impact basin, only partially filled with lava. You see these wonderful fractures and ponds of molten rock. Clearly a lot of interesting stuff happened here. And this is an area we can only just barely see the edge of from here on Earth. But this is one of the areas where we've got two good landing sites that we're looking at. On the far side of the moon, you don't have many of those seas that we see on the near side, but you do have this one, Mare Moscoviense. And as we look down at Mare Moscoviense, we see this is one of the thinnest places of occurrences of lunar crust. We see examples of those lunar swirls. We see volcanic ash deposits. There's a whole lot going on here. Also on the far side of the moon is an ancient, huge impact basin, the South Pole Aitken Basin. We'll switch to a laser altimetry view, and you can see that great big dark low area there, about 2,000 kilometers across. This impact almost destroyed the moon, and it probably excavated deep enough that it may actually expose material from the moon's mantle. This is the Schrödinger crater. And the Schrödinger crater is interesting because it has permanently shadowed regions where the sun never shines. It has volcanic vents. And flying down into the Schrödinger crater, we can use Moontrek to actually go roving along and drive right up to the edge of one of these volcanic vents. Okay, here we're finding another area that's kind of strange. This is the Compton-Belkovich thorium hotspot. And it's again an area of very thick, pasty lava eruption. And it's very rich in the element thorium. It shows up just glowing on maps, and we're not sure what in the world is going on there. Looking at the poles of the moon, here we're looking at the South Pole. You see deep shadows because the sunlight is coming in horizontally. Makes it really hard to plan a mission. But using Moontrek, we can use laser altimetry to pierce those shadows. We can do slope maps. We can look at where the permanent shadows are. We can look at temperature maps. All of this looking for water. Here's hydrogen abundance, looking at actually deposits of frost, and even ice, how far down you have to dig for ice to be stable. Again, this is really important because you use that water to have water to drink. You can use that water to break apart into its component hydrogen and oxygen. The oxygen you'll need to breathe. The hydrogen you can use as fuel. The moon could be our fuel depot for exploring the rest of the solar system. It's a lot easier to get the fuel here than from the Earth. Because the Earth, you have to go out of our very deep gravity well in our thick atmosphere. It's readily accessible on the moon. At least that's what we hope. So, again, I will invite you to make use of our portal. Now, what we've done here for the moon, we've also done for Mars. We have done for the asteroid Vesta, the dwarf planet Ceres, Saturn's moon Titan, 7 of Saturn's smaller moons, and we've got Mercury coming and a whole bunch of other worlds. So come visit the Solar System Treks and explore the solar system with us. Now, I'll just leave that up there so that just kind of gets burned into your mind. But again, our astronauts, when they went to the moon, they brought back rocks. The moon's a long way to go to bring back bags of rocks. Why would you go all that way to bring back a bunch of rocks? Well, as I like to tell kids at school, there are many different types of scientists at NASA. I was trained in astrophysics, but astronomers are not the only kinds of scientists at NASA. We're just the best looking scientists at NASA. But there are many other types of scientists, including geologists. And if you become a geologist, you learn to be able to hear the stories that rocks have to tell. Rocks tell us stories of how they formed, where they formed, when they formed, the conditions under which they formed. That's critical. That's neat. Now, here on Earth, we would love to find rocks that could tell us the earliest stories of those first days of the Earth. We are utterly dependent upon this one world we live on, and it's in our interest to know as much about it as we can. But we cannot find any rocks on Earth from the really early days of the Earth. Because here on Earth, we have wind, we have rain, erosion, we have plate tectonics that resurface the Earth, repave the Earth. And so as a result, we have no rocks that can tell us the stories of those earliest days. We only get about halfway back. Very disappointing. But we now come to understand that the Earth and Moon formed together in a giant impact about 4.6 billion years ago, when 2 planets tried to occupy the same place at the same time with predictably messy results. The heavy nickel-iron cores of both those worlds sunk together and formed the big nickel-iron core that we have here on Earth today. A lot of the lighter outer silicate rock got blasted off into space. Some of it was lost to space, but a lot of it formed a ring around the early Earth. Yes, the early Earth had a ring around it, much like Saturn. But instead of being made of ice particles, it was made of hot, molten rock. And then that stuff started to clump together, and it formed the moon. So the Earth and moon formed together. On the moon, there is no wind. On the moon, there is no rain. On the moon, there is no plate tectonics. So in going to the moon, we can find really, really, really old rocks that we cannot find here on Earth. And since we formed together, turns out one of the best places to go if you want to learn about the earliest days of the Earth is the moon. That's a fun story to tell. A few weeks ago, the story just got a lot better. We're still going through those bags of rocks that were brought back by the Apollo astronauts. Some of those bags have not ever been opened yet. There's still a lot of discovery going on. And a fascinating discovery was just made of a rock brought back by the Apollo 14 astronauts who went hiking up that ridge toward Cone Crater. And looking at one of those rocks in the laboratory recently, it was discovered that this one rock they were looking at just didn't fit. It wasn't right. It did not look like any other moon rock they had seen. And so they started listening to the story that this rock had to tell. And this rock told a story of how it apparently formed, not on the moon, but here on Earth, between 4 and 4.1 billion years ago, at a depth of 12 miles. Shortly after forming, it was excavated by a giant asteroid impact that slammed into the Earth and blasted that rock from the surface of the Earth out into space, where it then landed on the moon. And it sat there on the moon until 3.9 billion years ago, when there was another big asteroid impact on the moon. And you had this huge tidal wave of hot molten rock come screaming across the lunar surface, burying our little Earth rock. And there we would have presumed that it would have been lost. But then 26 million years ago, a smaller asteroid hits the surface of the moon, blasts a hole, and excavates our little Earth rock and leaves it sitting out on the surface, where now, just coming up on 50 years ago, astronaut Alan Shepard, the one who was still ruminating about lowest bidder, came walking along, saw that rock, picked it up, put it in a bag, and brought it back to the Earth. How cool is that? And so, what we seem to be seeing here is that what appears to be the oldest Earth rock we have ever encountered, the oldest rock from our own world, with its wonderful stories to tell, has been preserved for us on the surface of the moon. I think that's just way cool. So I see my time is almost up. I will hang out here and answer questions. And I have brought with me a rock from the moon. And so anyone who is interested can come up here. We have this nice little magnifying dome so you can look down and you can see details in this rock from the moon. But even better, if you make your hand nice and flat, you can reach in here and you can touch a rock from the moon. That's right, you can touch a moon rock. And I'm here to tell you that you can do that safely. There are no ill effects, though I must confess I did start out the week as a 28-year-old woman. So if there are any questions, I'll try and take them now, and then I'll also hang out.
Thank you, Brian Day.